Of course, the A star algorithm has an exponential memory, and the equivalent is called as the iterative deepening A star algorithm. You apply the cost limited DFS where the cost will be on the F value rather than the G value. So if in your depth first search, a node has a F value which is more than the limit, you just prune it. So I'm not going into the detail for it. There's another algorithm called as a pure or a greedy heuristic search, where you take Fs is equal to H of S. You don't take G of S. So if Fs is equal to Gs, it is uniform cost search. If Fs is Gs plus Hs, it is A star algorithm. If Fs is equal to Hs, it's called as a greedy heuristic search. In a greedy heuristic search, all that happens is you try to go in a greedy manner as close as possible to the goal. It's greedy, so you've been doing this questions in greedy programming. The only thing is it's with a search background. So in a typical greedy approach, you don't backtrack. Here you have the option to backtrack as well. It performs the best, shortest computation time, except for it is obviously not optimal. I'll let you do it for the last example and see for yourself that a heuristic search is never optimal. And because it's never optimal, we really don't end up using it, even though it gives the fastest results. So what is it? You see something close to goal, you just go at it. And because you just go at it, you reach the goal very fast, but you reach it with a wrong path or a suboptimal path. So use this formula and repeat whatever example I gave you. And of course, you've got many versions of it which are in between the iterative deepening A star, which is a pure DFS implementation, to the ones that try to manage the memory a little bit better. So these algorithms will say that, okay, run a normal A star algorithm. When you're about to lose memory, when you're about to go out of memory, they will let a memory manager sit. Okay, you all go away. If I need you, I'll calculate them back. So you prune nodes which have too large cost from your entire search tree. So you're pruning, so you get some more memory and you continue the search over there. So some wonderful algorithms over there. And that is what makes these algorithms really good. Now, the final topic that, of course, I will touch upon very briefly is practically what happens. So, practical. You make a heuristic function using all the methods that I told you, relaxed problem method. Now it turns out that the relaxed problem methods, the heuristic functions, are so bad, it's just worth the difference of bidirectional search versus a normal search. So they can just double your path. However, so if searching solutions till a depth of 10 was possible, now searching solution till a depth of 20 would be possible. That's all. And most of the times, believe me, that's not good enough. So I give a question every year in AI, and I can only give solution till depth 3, 4, 5, 6, and 7. After that, what happens is the number of states explode. So you either run out of memory, or if I say that, okay, use limited depth first search, iterative deepening, iterative lending, those solutions, you run out of time very quickly. So practically these searches do not make a lot of sense, and you still need to do something better. So you still need to search, and you cannot tell the master that, see, I am the best algorithm possible, I am still exponential complexity. So there's a limit of the depth of the solution depth that you can give me. I'll not just take anything. The master will say, you're supposed to do it, you're supposed to search anyhow. So we really need to make an extremely good heuristic functions. People started off with what are the pattern databases. So what means is that let humans solve a lot of problems, store the solutions. You yourself will solve so many problems as a search algorithm, and say that in an 8 puzzle problem, whenever 1, 2, 3, 4 are arranged in this manner, then the solution cost is approximately 8, irrespective of what these things are. So you mine out all these patterns and store it. It'll be much better than all the Manhattan distance, misplaced style, and everything else. Now, in a modern day solution, of course, the problem is saying it theoretically, that's okay. How do we do it practically? So in a modern sense, what we say is, whichever puzzle, whichever game, whichever AI question you are solving, let a lot of humans solve them in the form of a video game. So give it as a video game. You'll get so many people playing your game. They'll feel happy about it. They won't even know they are contributing towards your database. And make in a database state and cost to goal as calculated by human expert. Human thinks that human is solving a puzzle. Poor guy doesn't even know you're making in a database, and make this database. You know how do database populate? Just keep on populating databases. For one state, if you get 2 solutions by 2 different people, store the best one. So, and give it a nice GUI so that people really invest their time upon you in your database. Now make a normal machine learning system that, given this input, calculates this output. If you're from a deep learning background, you can give the entire 1 to 8 permutation. Deep learning can learn anything. The entire problem configuration, the entire whatever, and the cost comes as an output. If you are from classic machine learning, you will have to extract features. You have limited thing to do, and just learn that up. So, if you want to know how to use, why to use machine learning, take any of the problems. In fact, you talk about computers playing all the games. An example that I'll give you again, when we look at competitive learning, adversarial search, they're trying to estimate exactly the same thing. How far are they? And if you solve it by machine learning, you're solving a pretty similar thing. So, using deep learning and using shallow learning and using learning for the learning of a heuristic function is of course good. The only problem is this is made by the human. This is not the best. This is not technically admissible. So one way to say it, just discount it. Learn it by machine learning. Take 90% of that value and use it whatever that turns out to be. But that still may not be admissible. The other one is you'll get a little bit of a suboptimality because it's not admissible, and that little bit of a suboptimality can always do, so you can treat with it. And that is exactly what is soft computing. You get rid of strictly correct answer and optimal answer. You say little bit of suboptimality will do, with the caveat that you'll get an extremely big computational benefit. Okay, so we started off with some aspirations. It's a good time to see what do really these algorithms do at the end of the day. So the problem is, in a binary grid map, I just need to go from a source top left to the goal bottom right, and whatever states I explore, they are in my closed. I'll just color them to look at graphically what the algorithm is doing. So that's the A-star algorithm with convex obstacles. And as you can see, what it's doing is taking the elliptical search route. That's the source. So it's taking the elliptical search routes and therefore it barely explodes and it gets straight to the goal. Something happens with the A-star algorithm where I place a convex obstacles around it like this. Now for this node, it believes that its distance to the goal is straight here. In reality, the distance to the goal is all the way up here. Now remember, the complexity is exponential to the heuristic error. And look at how large the heuristic error becomes. It becomes massive. So you see that slowly what's happening over here, the algorithm is virtually exploring everything because the heuristic error has gone so large because of this concave obstacle being a bad representative. That's what concave obstacles do. This place, you can go directly to goal. In reality, you need to take a long route. So now it's almost a uniform cost search. Until now, the heuristic error again reduces because the concave obstacle problem has ended and you see it going around over here. In contrast, if you look at the uniform cost search, it's exploring that in circles. Okay, why is this not really a circle as per the description? Because for this source, this distance is exactly same as this distance. So the little uncircular region is because this difference from circle is what extra effort was put over here to circumvent the obstacle. So it's circular in terms of distance from the source. Visibly it's not exactly circular over here with a little deviation because these nodes around over here had obstacle avoidance as well. So it was roughly in a circle. And that's exactly as you would expect. It explodes the complete space. I bounded it so that it doesn't go back by a map boundary. And exactly the same thing around over here. You see it's exploring everything which is possible. So concave, convex, it was always bad. Concavity does not really hinder much. That's heuristic search, extremely fast. It's going greedy. It'll never backtrack. Heuristic search, so fast. However, now it needs to backtrack. That's the same heuristic search with a concave obstacle. Now it's going as close as possible to the goal. All the paths are because of obstacle, and the moment it gets out, now greedy is possible, and that's exactly what it gets. So that's what I end up with a nice funny video which shows what different algorithms in a 2D space are really doing and how much efforts are they putting. A caveat here, of course, just a 2D with a low resolution image is the easiest. In reality, no search is that much of a toy problem as well. But it's a nice illustration about how much of the search space do different algorithms really end up exploring. So that'll be all for the day. It's really getting late around over here. Have a great time. Thank you.